Okay, so we're going to look at one tutorial question that will apply the equation that you see on the screen right now, which is the momentum equation. Okay, so this will be the same as your handout or chapter 3.
Sir,
Oh,
don't have the screen.
oh, sorry. Let me share the screen. Now you see the screen, right?
Yeah.
Okay, so this question will be the same as your hands out or your tutorial, chapter 3, question 18. We'll go through this example in this session. So again, we'll go through this, we will see the application of these two equation. Yeah. So we're going to see the application of these two equation, or you can just memorize the first one. Okay. Okay. So let's say we have a stationary nozzle on the left, and this nozzle is spraying water to the plate here, and the water leaves the nozzle at 15 meter per second. You're given the area of the nozzle, which is in meter square. In test or in assignment or final exam, we will change the unit here. You need to convert it back to unit SI. So assume water is directly normal to the plate. So means if the water spray out and then hit the plate here, it will go 90 degree to the plate here. Means it will hit the plane at normal direction and then flow around the plate. Once the water hit this plate, it will go up and down. Determine the horizontal force that you need to resist to hold it in place. Means you need to find what is the force you will feel from the nozzle. Okay. Now this kind of question is quite straightforward, where you pull out all the known parameter from the question itself. So in this case, you are having a nozzle and plate, and since we deal with vector, you change all the entity. For example, velocity with the direction, the unit vector. In this case, because our nozzle is spraying to the right and is in the x direction, yeah, we assume to the right is x direction. So we will input as 15i hat, which is the unit vector for x direction. And the nozzle is given 0.01 meter square. And we need to find what is filled by the hand over here. Solution is that you need to know the direction of the velocity and the velocity after it hit the surface over here. Once go up, one go down. So there's a change of direction, x direction to y direction. Yeah, the water change from x direction. When it hit the plate, it will change to y direction. So the momentum switch place. So there are two methods that you can deal with these problems. I will show you these two methods. So one is that you use the first control volume like you see on the screen here, meaning you draw the first type of control volume and you analyze what is happening inside this control volume. The second one, you can choose to only focus what happened in front of the plate, where the second one is more favor. I will recommend for the second one, but I still need to show you the first method here so that you know that there's an alternate method to solve problems. Again, there's a difference between the control volume that you choose. However, the final answer will still be the same. All right, so we look at the first control volume first, and then we look at the second one. We will, in order to solve this kind of question, we need to use two equations, meaning with a combination of what we learned in a continuity equation, which is your m dot, the mass flow equation or continuity equation, and the one that we just learned, the momentum equation. Like what you see on the screen here, you need to know how to identify them. You need to know which one is conservation of mass, which one is momentum equation. Yeah. All right. So I'm going to ask question right now. By looking at the screen here, you have a two equation there. Are you able to identify which one is which one? Okay, so this question will go to Amel. So Amel, which one? Okay, I'll ask you, the first one here is which equation? It is conservation or momentum equation?
It's momentum.
Momentum. How you know it is a momentum?
Because of the I have the okay.
What's the formula for momentum? How
So
you
it's
find
MV or T.
MV? Yes, correct. So yeah, the question the answer is look at the momentum equation. So you call out the physics or the fundamental equation for momentum, like what you say just now, MV. Good job. Huh? So you have a MV here. So this is the first one. So the second one, if you do the analysis here, you take the rho times the volume, you get mass. So it's quite straightforward question. So again, in the exam, don't panic. Just look for the correct equation. All right? Don't confuse between these two. These two is quite different. It's quite different. One with the additional V, one without V. So the difference is between there's additional V for momentum. For mass, there's no V. Mass is only have mass. But when you talk about momentum, there's a mv there. So there's a velocity vector inside the equation. Okay, let's start to solve already. We have three assumptions in this question. First, we will have a steady flow. Second one, we have an incompressible flow. The third one, we have a uniform flow. So you have a steady flow. Once you have the steady flow, you can cancel out something in the equation straight away. So the first, in exam, you write these two equations out, you get 1 mark. Then you write the assumption, or you can straight away, if you have assumed that it's a steady flow, or you see a steady flow inside the question statement there, straight away you draw an arrow for the first term, for both, for momentum equation and continuity equation. The first term, you draw an arrow, and then you write steady flow. Why steady flow? You can cancel out because anything that you take the volume or density, you divide it by time, you get 0, right? Because if you have steady flow, there's no acceleration, there's no change of velocity. So the first term becomes 0. So straight away draw an arrow, you write steady flow, you get the second 3 marks here. It means yeah, you get the second 3 marks, 1 mark. And then you draw a second arrow for the continuity equation, and then you write steady flow, you get another marks. So by looking at the slide here, 3 marks already, you will score 4 marks. Just write out the equation and draw the arrow and write the steady flow. You will score 4 marks before you press the calculator for the answer. Okay, so it's very easy to score. Again, it's very easy to score for this module, right? Then you simplify the equation. And the first equation, or the momentum equation, will be reduced to the third equation that you see on the screen here. The force, you have body force and surface force equal to, you only have what happening in the control surface. Okay, yeah. So again, you see the sum here because we have a uniform flow. But if you write integration, also I'll give you correct. Yeah, if you write the integration at the right hand side here, I will still give you correct because it's still the correct concept. The second equation, you reduce to this form. So if you write integration, also I'll give you correct because it's just a simplification of the equation after you apply the assumption. Okay, so I think this slide is quite straightforward. Then we move on to solution already. The next one, once you have you apply the assumption, you look at the equation, and then you just go ahead and substitute all the known value inside there. Okay. You look at the control volume 1 here. So control volume 1 here, we will focus on x direction. Yeah, we will focus on x direction. So what you change the momentum equation on the top here. Since you're focusing on x direction, the v vector here you change to u, then the rest you copy. And in this case, because your flow is moving in x direction, again, body force is still with gravity. Gravity is pointing down, so there's no pointing down force here. Yeah, in this case, because your gravity is in y direction, and currently we are focusing on x direction, so there's no body force in x direction. Yeah, so don't confuse the direction. Now we are focusing on x direction only. Yeah, yes, there is a body force in y direction, but currently we only focus on x direction. So this statement is valid where we don't have body force in x direction. So you can cancel out the FP in the equation that I showed you just now. So you cancel out this one. Then you further reduce the momentum equation. You're only seeing surface force equal to momentum equation in the control surface called domain. All right, so stop me if you're not able to follow or I speak too fast. I will stop and try to explain what you don't understand. If you see something that it seems a bit blur, or seems anything that seems not logic to you, just stop me and ask me a question. Yeah. Okay, so we continue with the calculation. We reduce the equation on the top here to this form after we apply the assumption of all we have in the previous slides. And then because we focus on x direction, with the u term here, we know that focus on x direction, there's no body force there. Then we draw the free body diagram by looking at the control volume number 1. You draw the dot square here, and then you input all the force onto the free body diagram. So it will take some time to practice or to understand how to do it, but practice will help you to further understanding. So you draw the control volume, and then you start with the force. You start with the weight going down, and then there is RY component, the reaction in RY component and reaction to the RX component. You assume that you are having a fixed position, or that there's a fixture on the right hand side, means you fix something here. So you fix something here means that you will have a reaction force, that what you learned in your static module. Yeah. So if you have a fixture or something that cannot move, then you have a reaction force in x direction and y direction. Yeah, so now you should know how to draw the weight and the reaction force based on the control volume. And both sides, the left hand side and right hand side, both side is having atmospheric pressure acting on it. Pressure always pressing on the surface. So that's why the arrow is pointing to the surface here. All right. Now, why we do not draw the atmospheric pressure on top? why we do not draw atmospheric pressure on top. Okay, now because we are focusing on x direction, yeah, we're focusing on x direction component, so the pressure is acting on both sides only. Yeah, yes, there's a atmospheric pressure on the top and bottom, but again, it just shows that later you can cancel the one on the left and right. So it doesn't matter if you draw top and bottom also, it will still cancel. So we can write the surface force in x direction equal to pressure times area, you get the force because of the atmospheric pressure, minus negative because it's going against x-axis, negative pressure times area over here, plus Rx for the x direction. Then you can cancel. So your Fsx will equal to Rx, yeah. So this is just a further explanation of the pressure. Yeah, negative is because it's going opposite x direction. Rx is the force that you feel by your hand. We assume that it is positive, yeah. In this case, we assume it's going this direction. So you start with all the conventional direction, all the x to the right, all the x to the, all the y is going up. So later, if you find a negative value, it means that what you assume here is wrong. You need to reverse it. Need to reverse it. So we arrive at this surface force in x direction. Then you cancel out these two terms. You arrive at Rx. Then you have solved for the right hand side, the force already. Then you continue with the right hand side. You continue with the right hand side. You are equal to u rho v dot a. You have two vector here. Two vector here, and call out the concept that we learned previously. You draw the opening and you draw the velocity, then you know whether it's positive or negative. Yeah. Okay, so before we move forward, okay, I think so the next one you have u rho v dot dA1, which is position number 1 here. So let me ask this question to Ku. Let's say this is position 1. What do you think the products of v dot A at this location or along this line? What do you think? You'll get positive or negative? The dot products. V vector dot A vector. What do you think, Ku?
Positive.
Why positive?
Because the v direction is going
Left. All right.
yeah,
Going left or right?
right.
Going right. The V direction going right. What about area? Area going where? This is number 1. Area going where?
Area also going right.
Area going right.
Yeah.
Okay. So this is what you understand from what I teach just now. Okay, I'm going to ask Oliver. Oliver, what do you think? What do you think about the direction of A1? What do you think? Do you think it's also going to the right? How do you draw the vector of your area? You go to the right or go to the left?
Should go
Area.
to the right.
Go to the right, this one.
Yeah.
Okay. Amir, what do you think, Amir? This question asks to go to Amir also. Amir, what?
It goes to the left, sir.
Yeah, go to the left. Why? Why go to the left? Try to
Because,
explain to Ku and Oliver.
so let's say that this is a control volume. So
Yeah.
each side goes to like the upper side goes to up, the down side goes to down. So the left side goes to left.
Yeah. Okay. So again, recall the concept. Ku and Oliver. Don't make this mistake in test. We always look at opening. Okay. Look at opening. So let's say this is your opening. You always draw with area first. Area always pointing out. This one, let's say you have an opening. The area always pointing out.
So the area is opposite to the opening. Opposite
if you-
direction to opening.
Yeah, so if you look at this diagram, I remove all my marking here. If I remove all my marking, you look at this area. This is opening. So the area is pointing here. Okay. Understand not, Oliver and Ku?
Yeah, understand.
Yeah.
Then you input the volume like that. So now you take volume, not volume, velocity times the area, you get negative. Understand not?
Yeah.
Now you understand,
Yeah.
Okay. Cool. This question also for you. I ask you another side. So
Okay.
what happened to another side? What is the area going left or going right?
Right.
Why go to the right?
Because the
Because it's facing what? Facing which direction?
because it's facing the
Facing to the left or right?
right.
Facing to the right, right? So your A is this direction, yeah?
Yeah.
Okay. So just let you know. And then what about the velocity? Where the velocity go for control volume number 2 here?
Left.
Left. Look at the system. Where's the velocity go? It go up, right? Go up, go down, right? The water go up and go down, right?
Yeah.
So there is no left, right. It's go up in this case. Go up or go down. So there's a velocity is going up here. So there's a 90-degree. So you won't have anything on the right for the dot products. So just let you know. So okay. So enough for the explanation for the dot products. Okay. So top and bottom surface, the velocity will be 0, right? Because top here, there is no x direction velocity. You only have y direction in top and bottom. The water go like this way, so there is no x direction. So I can write my equation. Okay, I can write this equation as negative u1 rho v1 a1. So in this place, at this time, you should know why there's a negative there for point number 1 here. Okay. Then the rest is just substitution of all the parameter. U is given, rho is given. If you're not given, you refer to the appendix A. Then for water, it will be 999. Velocity 15. A is given. So you calculate, you get a negative 2.25 kilonewton. So what does it mean if you have calculate negative 2.25, and in the diagram that you draw, you're drawing Rx is to the right. When you calculate, you have a negative sign. It means what you draw here is wrong. What you guessed earlier is wrong. The real direction is to the left, yeah? Rx is to the left. Okay, understand, huh? Understand why if you have a negative, your Rx, you need to flip to another side.
Yes, sir.
Okay, then what you feel in your hand will be on this side of the diagram. So it will be a negative Rx. Okay, what does it mean? It means that what you feel over here is your Kx here. Your hand is over here. So it will be to balance the Rx, there is a negative, there's a opposite direction that feel by the hand. The hand is given by Kx. So you write Kx equal to negative Rx, you substitute negative 2.25, you get positive 2.25 Newton that you feel in your hand. Act to the right. The force is acting to the right. Okay. Okay. Then the next second method, we will go to control volume number 2. So you apply the same concept. Now you draw the control volume number 2 with just a simple rectangular, and we are facing pressure force, pressure, atmospheric pressure. You need to convert into force. So you take the atmospheric pressure times the area of this side, get the force on the left hand side, and you have a force at the bx here, at the plate here. So there's a bx there. Then after that, you convert the diagram. You have two free body diagram. One is the control volume diagram. One is the plate over here. So you assume this direction is you assume one. So we always like to assume our force is always going along our axis. That's why we assume bx is to the right. All the direction in force we assume is going up. Yeah. So you draw one free body diagram for the control volume. Then you draw another one for the plate here. That you have then you input all the forces there. So to balance the force from the control volume, you will invert. If your CV Bx is to the right, when you do the free body diagram for the plate, it will be going opposite direction, just to balance the force inside the system. And then you'll feel the pressure, atmospheric pressure on the right hand side of the plate here also. And you'll have a reaction force for both Rx and Ry. So you need to draw this two free body diagram for the second control volume. Then we solve using the diagram. Again, we're focusing on the x direction. If you look at the diagram here, you will only have a P pressure times the area here plus the Bx component for your control surface. And then on the right hand side will be the momentum equation. So I will just show you what is the Fx, and then you input your momentum equation. So this one is your force component. This one is your momentum component. All right. So you should understand why it is positive in this case. Yeah. Why you have a not yet. You're still seeing vector. So you should understand what you get a negative 2.25, right? By using the concept that we learned in the previous control volume number 1. Okay, you should know how to convert this one into the scalar V1 and A1. So you get negative by drawing the opening and the volume. So again, this is the 1. You draw the opening, area going this way, volume going in. So volume dot area vector, you get negative sign. Again, always learn to draw the opening. Start with the area. See where is the surface pointing. The surface always pointing out. Yeah. And then you draw the volume. You combine these two. You look at the arrow. If it's opposite direction, then you get negative. If it go along, then you get a positive. Then for Bx, Bx will be negative of the pressure times area of the plate. Negative 2.25, because if you try to rewrite this equation, right, this one you put over here. Yeah. So you pull this term to the left hand side, you get your Bx. So your Bx equal to negative pressure times the area of the plate minus 2.25, which is the momentum. This is a momentum. This is the surface force, yeah. Then you calculate the answer. The next one, you know what is your Bx. Then the next one, you look at the plate free body diagram. You focus on x direction, so all the force in x direction equal to 0, where you have a equilibrium principle apply here. So you look at the diagram, Bx is to the left, you get negative sign. So you get negative Bx. Pressure times the area is to the left, so you get a negative sign here. And the Rx is to the right, you get a positive sign here. The rest is just rearrange of equation. Rx will be equal to Bx plus atmospheric pressure times the area of the plate. You move this term, these two terms to the left, you get positive term. The rest is just substitution. So you substitute back what is your Bx just now. Your Bx equal to this equation. Bx equal to negative pressure area minus 2.25 plus atmospheric pressure times plate. After you look at the equation, you can cancel the pressure area term in the equation. You will still get the same answer, negative 2.25 kilonewton. And the force felt by your hand is opposite by the reaction force of Rx. So you will feel 2.25. The force is, because it's positive, and we assume all the force to x direction to the right is positive. So based on your calculation, you get positive, means the force is acting to the right on your hand. This is how you explain your answer. Okay, so I stop the recording.